A couple of logistical announcements before Lynn's talk. We are streaming this live on YouTube, and the recording of that will be available afterwards for you to view on YouTube. So if you miss any part of the talk, you can go back and watch it on YouTube later, or of course, recommend it to your friends. There will be an opportunity to ask questions afterwards, and if you've got a question you want to ask, if you could click on the Q&A button at the bottom of your screen, and you'll be able to type in your question at any time, but we won't look at those until after the talk. We'll have a separate Q&A session at the end. So with that, I think I will hand straight over to Lynn. And I need to stop sharing my screen so she can share her slides.
Thank you. Right. Yes, that we have it. Hopefully you can all see the first slide that we have up. Well, good evening. Although that we are now at solar minimum and sunspots are quite small and pretty rare, it's still a very interesting time to observe the solar cycle. And that is because we're just finishing one and starting another. And in fact, we've got sunspots from both cycles on the sun. Or rather, not today we have, but we have had and hopefully we'll have in the future. So tonight, what I want to do is to have a brief look back at solar cycle history and just see how we've got there to where we are today. And then we want to look again at cycle 24. It's been quite a low energy cycle compared to some of the previous ones of the last 100 years. But that doesn't mean to say that it's not without its highlights. So we'll have a look at those. And then we'll have a look at the first signs of the new cycle and see, well, how can you tell it's a new cycle spot from the old cycle one? And then look forward and see what we might expect for cycle 25 in the coming years. Now, as you know, in astronomy, you want a large aperture telescope because you're looking at pretty small things a long way away, and the idea is to gather as much light as possible. Well, with solar astronomy, of course, we have a very large object. It's relatively near and it's relatively bright. So we need a small telescope, which is good news if you've only got a small telescope. A small refractor is ideal for projecting the sun through onto a piece of white card or into a projection box. This is what I use. I used to use a refractor and project onto a piece of white card, but sadly, as age goes on, one's eyesight isn't what it was. And I find that using a direct viewing method like this is far better for teasing out the small details, particularly small and faint spots that we have at the moment. So this is a Celestron 5i. It's a 125 millimeter telescope, and I have fitted with a glass solar filter here. Obviously, at this point, I must just caution anyone, you must never look through an unshielded or unfiltered telescope at the sun, nor even look at it naked eye, because you can, of course, damage your eyesight from the radiation. So always safety first. I always have a particular safety routine that I never vary from every time. I once projected the sun and burned my thumb changing an eyepiece, and by Jove, if you do that once, you'll not do it twice. So I'm very, very careful. Right. We were looking, obviously, in white light at the photosphere. The sun is a gaseous object, but at the photosphere is where light is released. That's where we see sunspots. And it tends to look solid when you look at it. We refer to it as the solar surface. That's what it looks like when I'm looking through my telescope. So that's what a glass solar filter will give you. And it's very much like what we're looking at the moment, no sunspots at all. But it gives you a very pleasing yellow sort of colour, and there's good contrast with sunspots. You can buy a material called mylar or barder film and make your own solar filters if you're pretty good at DIY. And it's an awful lot cheaper to do that. And that gives you kind of a silvery image, but it's just every bit as good, even though it's a lot cheaper. Now, the real expense comes is if you want to look at the solar chromosphere. That is the atmosphere of the sun. And with that, then you need a dedicated solar telescope, or you can buy a filtering system for your own refractor, which would mean that you get a H-alpha filter over the objective end and a blocking filter over the eyepiece end. or you can get there a dedicated telescope, as I have there. That's a Coronado Near Star, which is a 70mm. Quite expensive to buy, but both systems are quite expensive to buy. But when you consider I've had that for nearly 20 years now, then it's been good value per year over that time. So it's only a one-off purchase, hopefully, anyway. And that enables us then to have a look at the solar atmosphere, and it's targeting a very narrow band in spectrum towards the red end of the spectrum. And that's why you have a red disk. You won't see the sunspots quite as clearly as you will in white light, but that's not really the point, because we're looking at the magnetic area over the top of sunspots. So there's our sunspot, and here we have a filament, which is a strand of plasma which is suspended in a magnetic loop, and you're seeing it dart there as against the brighter background of the sun. But they also occur as prominences. Maybe you see a faint one there. So that is, again, is plasma is suspended here. You can see it arcing out into the darkness of space. And so it appears bright against the dark background. But they're actually exactly the same thing, or we just call them something different. So that is a filament, and that's a prominence, but basically it's the same thing. Here's another setup. I think that's Ron Johnson's setup, another member of the solar section. And you can see it has a rather nice refractor, again fitted with a solar filter, and it's piggybacked on their H alpha telescope. And he has a CCD camera and obviously a sheltered laptop there against the glare of the daylight, so he can do some imaging. So it's like anything else. In solar observing, you can have a small, quite cheap telescope, nothing too fancy, and to get started. But then as time goes on, you get more interested and you get more gear, and it can really be just as expensive as you want it to be, like anything else. So let's have a look then at the solar cycle and see what we actually mean by the solar cycle. You might wonder, because we're just ending solar cycle 24 and about to start solar cycle 25. And I think, well, if the sun's 4.5 billion years old and the solar cycle is 11 years long rather, how on earth do we only get to 24? Well, I'll explain that in a wee moment, hopefully. So this shows you some of the recent cycles we've had, and there's the one we're just ending. This is cycle 24. And you can see straight away it's a bit different from the others. It's been quite a low intensity cycle, but that's not, again, too unusual, although it has been the lowest intensity cycle for the last 100 years. So we have high activity cycles, middle of the road ones, and low ones as well. In this one, you can see, well, you can see in them all, you can see there's double peaks, and that usually tells you the difference between northern and southern hemisphere activity, which can be different. You can peak on one hemisphere and then peak on the other. With this one, it's been the first one that we've managed to observe where the first peak has been lower than the second. Usually the first peak is the highest of the two. So that's just been a wee bit different, a bit unusual. If we look back in time, we've been looking at or charting naked eye sunspots way back to about 800 BC, because the Chinese astronomers obviously didn't have a telescope or anything like. They were noting down sunspots. But it wasn't until the telescope was invented around 1610 that Thomas Harriot first turned his telescope on the sun and started to see sunspots. Samuel Schwab in 1843 was the first guy who noticed some variability in sunspots, that they were plentiful at one end of a 10-year cycle and not quite so plentiful at the other end of it. And what he was trying to do was to discover a planet that existed between Mercury and the sun. And so in order to do that, he was charting in some detail sunspots, trying to spot this mystery planet. Of course, he failed because there was no such planet. But what he did discover was variability in the sunspot cycle, which he reckoned was around about 10 years. Rudolf Wolf came along about the same time, and he not only analysed his own sunspot observations, but those of other astronomers. And he discovered that was a variability of around about 11 years. And what he decided to do was to catalogue them. And that's why the sunspot cycle starts where it did, because he charted things back to about 1745, but he found that the real cycle, the real minimum started, and then a first 11-year cycle went on to 1766, and the first one was 1755 to 1766. So that was the first full cycle that he recognized from observations. Now you can see there that the sunspot cycle isn't exactly 11 years long, not by any means at all. In fact, we have two quite short ones there at 9 years and 9.25 years. Interestingly, they are the shortest ones on record, and then followed by the longest one on record at 13.67 years. All the ones after cycle 6 up to present day have been around about the 10 to 11 years in length. Now, this diagram just superimposes over the solar cycles that we've shown you, the latitudes of sunspot. This is called a butterfly diagram. So you can chart when sunspots begin at solar minimum that we're starting to see now. You'll find that in the northern and in the southern hemispheres that they appear at quite a high latitude. And then as the solar cycle, the 11-year cycle, goes on, you will find they will start to migrate in towards the solar equator. And that's a pattern that is repeated every cycle. Cycle sunspots, they usually appear around about latitude 25 to 30 in both hemispheres. And then they migrate in towards the equator. But interestingly enough, they can coexist with sunspots from the old cycle. And that's what we're seeing at the moment. So we have the old cycle spots, which are near the equator, probably around about 5 to 7 degrees in latitude. And then we have the new cycle spots appearing higher at sort of 25 to 30. They can coexist for a year or two, but around about 18 months after the old cycle ends, the new cycle spots then suddenly go up slightly in latitude, which is what you wouldn't quite expect. But they go up to about latitude 30 to 35. Some of them have even been charted in the past at around about 40 or even 45 degrees in latitude. And if you're an observer, these are worth noting in your log. They've even been noted around about 70 degrees in latitude, but that is extremely unusual. They're never found at the poles, and they are rarely found at the equator, although they have been seen in the recent cycle to straddle the equator. So there's never with the sun, it never does. It does whatever it wants to do. So how do we tell then that an old cycle and a new cycle spot apart? Well, the sun has a magnetic configuration, which won't come as a surprise, but in each hemisphere, it's different. So let's say at the moment we have a sunspot here, which is a magnetic area. It has a dual polarity. So a sunspot will appear with, say, a negative and a positive polarity in this hemisphere, or that would be reversed in the other one. It'll be positive and negative. And then after the 11-year cycle, it flips around for the next 11-year cycle. So the northern hemispheres will be positive, followed by negative, and the southern will be negative, followed by positive. Some people say, oh, well, actually, there's a 2 cycle, not 11. And if they're saying that, then that's what they're referring to, that the sun takes 22 years to return to its magnetic configuration. Let's look back at solar cycles as far back as we can, and let's see if we can discern any sort of a pattern. Well, probably straight away you can see that there really isn't. But what we've had for the last 100 years or so is fairly high activity called a modern maximum. And then if we go back far enough, back to the 1800s, we'll see that solar activity died off very much for a couple of cycles there, and we call that the Dalton minimum. But then if we go back here to 1700s, 1645 to 1715, the 70-year period, where hardly any sunspots appeared at all. And this is quite famously called the Maunder minimum, where they only had enough sunspots in 70 years that we would experience in one modern year. It's pretty grim, really. From 1645 through to 1705, at any one time, there was only observed to be one sunspot on the solar surface at a time. Aurora were quite rare. They were certainly much reduced, as were sunspots. Sorry, not sunspots, naked eye sunspots. I think there's a question about this time we might tackle a bit later on about the Thames freezing over. And yes, it did do so, but there is no direct link. It would seem that the cold winters were only experienced in the northern hemisphere, not in the south, which would be unusual if it was due to lack of solar irradiation. So I don't think there's a link. I think there was also a volcano as well that could have been responsible for the freezing over in the cold winters around about that time. But basically, no one knows. There's no evidence either way, so we still can't answer that question. Going back even further then by carbon dating, so here we have our modern maximum, the Dalton minimum there, our Maunder minimum there. Then by carbon dating, we can go back and we can see we have other minima as well. And of course, we have high peaks of activity too. Is there a pattern? Well, other than saying that there are dips, troughs and peaks, then not really, because there doesn't seem to be any particular pattern between them in numbers of years, nor to the depth of which they go to. So that seems to be fairly random. So we don't know. But considering, again, the sun is 4.5 billion years old, and we've got 1,000 years worth of history there, it's a blink of an eye. So it's not a lot of material to work with to say what the sun is doing long term. So let's have a look then at some of the highlights of cycle 24, because it certainly has had a few. I've got a short sequence here by Kevin Kilburn, so I'll just play that for you. And we're looking at this sunspot here, rotating around the eastern limb. And just watch its development. I'll just play that for you again. So you can see there's been a tremendous amount of development there. I think that's sort of the thing that really got me into solar astronomy in the first instance, because you can see a sort of innocuous looking sunspot, and within 2 or 3 days, it can develop into something like that, which is just the interest of it. You just never quite tell what's going to happen. And sometimes you get a really interesting looking sunspot will come around, you think, oh, that's going to develop, and it doesn't. It can be quite benign. So you never quite know from day to day what's going to happen. Now this picture here, this image was taken by Cheryl and Carl. It's back in 2011 November. Now this is a sort of bluish color because this is what we call calcium Kaline. It's a layer, it's a cooler layer just underneath the H-alpha line that we've been talking about and above the photosphere. And what it shows here is it's very good at producing the, showing up in a bright light, the chromospheric network. And this brighter area here is calcium plage. So sometimes it's bright enough to be able to show you a prominence, we won't have any in this particular instance, but you don't see any filaments. So different bands of light, then you can see different features in the sun. But it just goes to show you the extent of that particular sunspot in calcium plage. This is the same sunspot here, taken in H-alpha. So again, that narrow band, but towards the red end of the spectrum with this. And so here we got the filaments are popping out. And you also see some brightening in there, some bright plage and probably some flares coming out of that region. And there is a sunspot. It's straddling the central meridian, what we call central meridian down the sun. And it's at this point, if we get solar flares from a sunspot region like that, that they will be Earth facing. And so we can look forward maybe in 2 or 3 days time, if we get a solar flare from that, we can get some decent aurora. And that's a sunspot in close-up, so you can see it's quite complex. It's an active region, that's what AR stands for, 1339. And this number was brought into being by the Americans in 1972. So we've had an awful lot more than 1,000 sunspots since then. It's quite a long number, but for brevity, we just use the last 4 digits of the number to identify the sunspot. You'll see here it says it's a type FKC. Well, we categorize sunspots into A for the very smallest type of sunspot, really just a small single sunspot without any penumbra. So this is the umbra, this is the penumbra. So it wouldn't have any penumbra around it and it'd be quite small to be just an A type sunspot. and then B, and then C. C is growing. It's a single sunspot, but it's got a penumbra. And then we go all the way up to F, which is this highly complex sunspot group. The rest of it is just describing the type of group it is. So if you want to know any more about that, I have written an article which you can find on the BAA website, and it's called the Q or quality number. We measure the size, and we measure that in it's in millions of solar hemisphere, and this was 1600, so it's quite a decent expanse. And Peter Meadows will be joining me a little bit later for question and answer. So he's got some software, I think, that will measure this, so you can ask him about that. And this sunspot was visible to the protected naked eye, and that just means holding a solar filter up to the sun and simply looking through it. And if you can see your sunspot through the solar filter, then it's P&E, visible to the protected naked eye. So in July 2012, we have another quite large sunspot came around the southeast limb. Let's just watch its progression. So you can see there, if I just play that again, tremendous amount of development there. And these images are courtesy of Kevin Kilburn. So much so that Damien Peach, who is a rather good imager, to say the least, turned his attentions and he came up with this magnificent photograph. So here we have the umbral area and here the penumbral area of the sunspot. Now, a sunspot is just caused by magnetic fields, and they suppress the rising plasma that is coming up onto the solar surface. So it's, although it looks dark, it's about 4,000 degrees centigrade, and the surrounding material, these are called penumbral filaments, not to be confused in any way with H-alpha filaments. And then the photosphere around it here is about 6,000 degrees. So that's why it all looks dark by comparison. The ancients used to think, of course, there were holes in the sun, but they're not at all. When you get sunspots near the solar limb, they show an effect called the Wilson effect, which shows them they look like they've got a dip in them, but it is just a visual effect, and they haven't actually got a dip at all. Now, around here, you can see the photosphere. We have the granulation there, beautiful photograph. Now that's a close-up of the granulation, and what that is we've got the hot material rising from the solar interior, and it's released then at the photosphere surface in these granules. And then once the energy is released, the cooler energy, the cooler plasma, goes down through these dark intergranular lanes to be reheated and then to be brought back up, and that's how it all works. Deep down then, in the convection zone, we have a kink in the magnetic field from time to time, and these are called flux tubes. And when these pop up through the photosphere, they pop up as very bright little dots, and these are called filigree. Now, sometimes these flux tubes are a lot larger than that, and when they're larger, they're darker. And when they appear on the photosphere, then they can develop into a rudimentary sunspot called a pore. And it's these pores that can then develop into the type of sunspots that we're looking at, well, any sort of sunspot, but into these absolutely massive ones. This is a photograph by Dave Tyler, and it's looking at the chromosphere. So this is taken in H-alpha. So you'll see straight away that you're not looking at the sunspot in the detail that you were seeing it in white light, but you are seeing all the activity, the magnetic activity that's happening above and around the sunspot. And you'll see some magnificent filaments there, and some bright material here, which is H-alpha plage. And it's this area from which solar flares can emanate. Magnificent disturbance around there as well. It's quite another magnificent image. And Damien turned his CCD camera onto that same sunspot 2 or 3 days later down the line, and you can see some progression with it there. Now, these here are where the The filaments here are growing across, the penumbral filaments have been growing across, extending across the umbra, cutting it into 3 portions there, and it's another one here. Looks like that's going to sort of grow out as well. These are called light bridges, and they usually occur when the sunspot is in a period of decay. So that's it, the sunspot is probably going to break up over coming days. And here we can see that same group in H alpha, just as it's about to rotate over the western limb. Again, it was an F-type sunspot, so one of the largest sunspots as you would expect it to be. And it was heralded by vast amounts of what we call faculae in white light. And faculae, they can be seen better near the limb where you have a limb darkening effect. And they are sort of white, bright clouds of magnetic material, which are weaker magnetically than a sunspot area, which is a particularly strong magnetic area. But don't mix up faculae with H alpha plage, because faculae is a white light phenomenon where a plage is not. So you can see this was nearly 1200 millionths of solar hemisphere in area, which is quite a reasonable size. And this spot was associated with many solar flares throughout its passage, as you could probably expect it to be. So in January in 2014, and 2014 was a particularly good year on this previous solar cycle, we have AR 1944 appeared again over the eastern limb. So let's watch its progression. Now, there it is. It's just past the central meridian, and you can see the extent of it. Absolutely huge. Another one up here as well, it's quite separate. If they're separated by more than 10 degrees, then you count them as separate sunspots. Now, this one, you'd expect it to be really active, and so it was. But this is the more dormant area, and in fact, all the action was really in this area here. So if we go forward and look in H alpha, then you can see there's your main sunspot and here's your followers. So this is where all the magnetic entanglement was going on. And as you can see, it's busily flaring away happily there. Some very nice filaments. You can see the sort of magnetic contortions that are going around here, filaments associated with it, and just some very nice prominences around the limb as well. That's a close-up of the sunspot taken by Dave Tyler. And here again, you can see the main sunspot, and there's some magnificent filaments coming out of it, and lots of nice bright flaring material. So flares are measured not only in their brightness, but also in their extent, in the amount of area that they cover. And here we have a shot of the same sunspot group, and it's just about to rotate of the limb. And this is a particularly nice shot here of a filament emanating from the sunspot group, and you can see it then rising up and going over the limb as a prominence. So that just demonstrates how it's exactly the same thing. Here we have a filament, and there it is out there as a prominence. Nice dark filament there, and a beautiful smoking chimney effect there of a filament, and again some flaring material. So it transited the disk on the 2nd to the 13th of January, another F-type group with a very complex and irregular leader, and it was nearly 1600 millionths of solar hemisphere in January the 6th, and 19 degrees in length. So an F-type group would be in excess of 15 degrees in length, and it certainly qualified. As you would expect, it was seen with the protected naked eye in white light, and it was seen as one spot on January 3rd, and quite unusually as 2 sunspots on the 6th, 7th, well, it will have been on the 8th as well, and 9th, it just had to have an observation for that day. So that's quite unusual that we have 2 naked eye sunspots within one group. Now this one survived on further rotation, and sometimes that will happen, particularly with large and complex sunspots that will last maybe 2 or 3 rotations. So let's have a look and see what it did. And it came back, it was given a separate AR number, 1944, but it was still extremely impressive. And as you can see, it was bigger. So still an F-type group, but this, it was 1620 millionths at the beginning of February. The same group taken in H-alpha shows you again flaring and also magnificent filaments coming out of it and all this magnetic contortion around it. We also have an absolutely beautiful image here in calcium Kaline. So showing you the chromospheric network, and it's showing you calcium plage associated with this group. And it just shows you the influence of the sunspot and how it snakes all the way. In fact, it's nearly across the entire sun, entire hemisphere there. I mean, just look at the influence that that spot is causing. And of course, another quite decent sunspot group up there as well. Now, it did survive a third rotation, but unfortunately, when it came back, it was a shadow of its former self. It was just a single penumbral sunspot, an H-class sunspot. So not a lot to shout about. Only 160 millionths of square hemisphere. Now, the last one I'm going to show you is my personal favorite, AR2192. And if you just take one look at that in relation to the entire solar disk, you'll get just an idea of just how extensive this sunspot was. But not only was it extensive, but just look at it. I mean, it's like a solar whirlwind coming in, or a hurricane. It just looked what it is, a contorted tangle of magnetic fields. And you just know, looking at that, you are going to get a lot of activity, and it didn't disappoint. So there it is, 2192. It was 2,750 millionths of square hemisphere. That's rather substantial. Obviously an F-type group again, highly complex and highly wrapped up in magnetic fields. And you can look and see the Umbra here, split variously by light bridges all over the place. And let's have a look at it in H-alpha. Well, here we have it in white light, and then in calcium Kaline, you can see the extent of the plage there, and in H-alpha here. And a rather nice filament, not associated, but all the same, worth a mention. Dave Tyler just caught it as about to rotate off, and look at that for a beautiful flare. Quite magnificent, and some very nice filaments there as well. So there we have it. In fact, it crackled, absolutely crackled with flares. Flares are classified. We have A, B, and C, or rising in intensity. C class start to get really interesting. Then it goes to M class flares, and then the highest of all are X class flares. Every category is measured in 1 to 9. So we'd have C 1 to 9, then it would go to M 1 to 9, and then it goes to X. But X can go as far as you like, so you could have X60 or X80 or whatever, God forbid. But this one cracked off a magnificent flare on October the 27th here, X6.7. And here Andy Devi has captured 4 of the separate X-class flares from that region as it went across the solar disk. The 22nd there is at 1.6. X2 on the 26th of October, 27th, and that's the M6.7, and an X2 on the 27th of October. Flares don't last terribly long. They're very intense brightenings, and they last only a few minutes. So you've got to be in the right place at the right time. I've seen many a flare. Unfortunately, I've not been lucky enough to see an X-class flare, so I've still got that to chalk up. And here it is, just rotating off the western limb here, seen in calcium Kaline, and look at the plage area surrounding that. It's truly substantial. And here is a white light image taken by Dave Tyler. So you can still see the contortions it's all wrapped up in there. It's on the 21st of October. Now, the interesting point here is this little bit of opaqueness here is called an umbral dot. And that's something you'll see in white light quite rarely. And really, it's something that you'll see more on an image rather than by just direct viewing. It's an opaqueness in the photosphere, and these umbral dots tend to appear right on the edge of the umbra and penumbra border, and that is beautifully illustrated there. Probably a little bit more than a dot, more an elongation, but anyway, there we are. So if you happen to observe any of those, then please do note that in your observing log. So let's have a look and see, well, what do we know? Well, we do know that despite cycle 24 being the weakest cycle since cycle 14, and that's 100 years, it still produced some remarkable active regions, which I think you'll agree. Now, generally, cycle 24 sunspots have been smaller than the previous cycles for the last 100 years. Cycle 14 to 22 all produced larger sunspots. But only cycle 23 failed to produce a larger sunspot than that beautiful storm we just looked at, 2192. But on average, all the sunspots in that cycle were larger than those of cycle 24. So we can conclude that cycle 24 was the weakest solar cycle for the last 100 years. On average, sunspot groups are smaller for 100 years, measured in millions per square hemisphere. And current observations show very little activity compared to the previous cycle. And that is the one thing I've noticed from my own observations to be quite outstanding. Last solar minimum in white light, as you would expect, there wasn't a great deal going on with sunspots. But there was certainly an awful lot more going in H-alpha. There's a lot of filaments, there was a lot of prominences, and this time it's been notably absent. Images have fared a little better. The CCD chip is more sensitive than the human eye, so they've produced some images showing activity. But when you're looking at it directly, then you just see very, very little, because what there is so faint that it's very hard to tease out. Cycle 23, that's the one previous to the one that's ending now. Let's have a look at the minimum there. So that went through its minimum in 2007, 2008, and 2009. So 11 years later, we'll look at the comparable spotless days that we've been looking at. So in 2007, 152. 2018, we beat it with 221. 2008, we had 268 spotless days, the deepest in 100 years. 2019, we had 281 spotless days. And in 2009, 260 spotless days. Well, so far in 2020, we've got 107. But there's still a good many to go. And if all the days between now and the end of the year are spotless, we might be able to beat this record in 1913 of 311 spotless days. But I don't think that's going to happen, especially with the new sunspot cycle having started. So I'll stick my neck out and say that that record will stay intact. And I think we'll see more activity than that. So in 2018, April the 9th, the very first active region of cycle 25 appeared. It was a southern latitude region at west 14, so it was just 14 degrees to the west of the central meridian, but there was no sunspot. It was just a magnetic disturbance, but it was significant because it displayed reverse polarity to the normal sunspots that had been appearing there for the last 11 years. So the new cycle had started. The first sunspots of the new cycle then, as we've seen, emerge about 18 months before the current solar cycle ends. Cycle spots appear around latitude 25 to 30, and then as the old cycle ends, they move up to 30, 35. A year later, July the 6th last year, we had a small B-type sunspot, so that's two sunspots traveling quite close together, neither of which had a penumbral area. And they appeared, and then they faded on the disk after a couple of days. First actual sunspot of the new cycle. So again, that was a significant event. So let's have a look at it. So there we are. Wow. This is an image taken by Mick Nichols. It's in calcium Kaline, although he hasn't coloured it blue. And you can just see the calcium plars and just about see one of the sunspots there. So that was active region 2744. You can see it here in white light. There it is, not very significant. And in H alpha, we've got a little bit of plage and disturbance there, and that was it. So it might not be much to look at, but it was significant in its own way. Then we had to wait until Christmas Day. And on the 25th, we had Ron Johnson, who then imaged AR2753. And that's a southern hemisphere spot again at South 29. So there we are. That's the classic B-type configuration, two tiny spots traveling together. And a very nice picture here from Gary Palmer showing that same sunspot group there in H alpha. So you can see a little bit of plage, which indicates a bit of growth and the magnetic contortions around there, but nothing really to shout about. Then we have AR2755, which came along in January this year. And there it is in H alpha, not too significant, but there we are in white light. You can see again another B-type group, southern hemisphere spot. That perhaps shows it a little bit better. At south 35 degrees, around about where you'd expect to find it. And there we are, a classic B-type group. And Nick James managed to capture the next one. That's at south latitude 29, and this is in March. So again, nothing much to shout about, but you can just see there's some little trailing pores just around there. And there's the image of that same spot taken in H alpha. David Strange took this one, and again, see there's some plage going on, so indicating some growth and the magnetic disturbance. And that's the same group in calcium Kaline, so showing the calcium plage. So not significant compared to what we've seen from the large sunspots of the previous solar cycle, but all the same, there we are. We have got some action going on. Now this one appeared on the 1st of July, 1st of April rather this year, and it was significant because it was a northern hemisphere spot. So that's the first northern hemisphere of the new cycle spot to turn up. And again, small B-type group. And there it is in H alpha, tiny bit of plage going on, showing a little bit of growth. So what do we know? Well, we know that old and new sunspots can coexist. Old cycle sunspots will be near the equator, and new cycle sunspots will be at between 25 to 30 degrees in latitude. Well, we know that, don't we? And then, the 27th of April, what happens? Well, we have an old cycle spot turns up south 7 degrees, which we expect it to be there. That's about bang on. And then we have a new cycle spot, and we know it's new cycle because it's got reverse polarity, and that turns up at south 17. And that's a very low latitude for a sunspot of the new cycle. So that in itself is rather strange. So what's going on there? And to bring you right bang up to date, just a couple of days ago, we thought we were going to have some action to show you tonight. Going back to white light, and we have some faculae here coming around. Might have to strain a bit to see it, but there's some faculae there as well. Now here's an image by Mick Jenkins, which you can probably see a little bit easier. He's taken the northern faculae coming around the northeast limb there and blown it up a bit, so you can see, and you can see the limb darkening there, then you can see what the faculae look like. And within that, we'll strain to find some small sunspots, but sadly there aren't. And I've been keeping my eye on it, and there still aren't any today. So this patch of faculae is kind of dwindled out a bit, but that tends to happen as it rotates anyway to the brighter areas of the sun. You don't see it so well. This one you can still see, but nothing in it. Still no sunspots have developed, but who knows? They might develop, you know, over time over the next few days, so we'll keep watching. And just to prove there is something there, I'm going to show you a very short movie from the Solar Dynamics Observatory showing those two areas, but this is in Hydrogenalpha coming round. So you'll see the northern area of faculae come around, you'll see the plage, and also down here. Interesting to watch the development as well of that prominence. I'll just play that for you again. So you can see in H alpha, you've got some real sort of activity there. It's far more impressive. So this is the current norm. This is what, when I get my telescopes out, I kind of look at more or less day after day after day. A nice blank sun in white light, same in calcium Kaline, and sadly the same here in H alpha. That's where the real difference of this minimum has occurred. But what will cycle 25 look like? Let's look a little bit into the future and see what it might, how it might develop. Well, deep down into the sun, we have a solar conveyor belt, and that determines the sunspot strengths over the next 20 years or so. And basically, decayed magnetic fields, they go down into the deep layers of the convection area of the sun, and they are re-amplified there and brought back up to the surface. So it's an important thing, this dynamo. Since the 19th century, it's been moving pretty much at a walking pace, so a very slow moving conveyor belt. But in recent years, not only has it decelerated, but it's also gone out of sync north and south. It's the slowest on record. And scientists are also able to measure the magnetic field strength in sunspot Umbra, and it's been steadily declining. If this decline continues and it goes below 1500 Gauss, then there won't be enough magnetic strength for sunspots to actually form. We will cross that line in 2022. So cycle 25 strength could be similar to that of the Dalton minimum. If that decline continues, we might run out of sunspots altogether. But having said that, the predictions of cycle 25 are that it will be very similar to those of cycle 24, and that won't happen. But of course, solar cycle prediction is notoriously up and down and not very good at all. And so what we do in the solar section, when you solar observer will do, is to obviously chart what's going on, to make solar logs and observations, and then in a few years' time, we'll be able to come on and tell you what actually did happen. So what will happen next? Well, in the famous words of Sir Patrick, we simply don't know. And that is the truth of it. But that's the joy of solar observing. We don't know at all. And as solar observers, well, we will log it and we will find out over the years to come. Now that just about brings me to the end. But before I go, I'd just like to bring you bang up to date. And I'd like to show you a drawing that's been sent in here, a sketch by Alexandra Hart of a very recent prominence that she observed on the 6th of May, and what a beautiful drawing that is. She also sent an image of that same drawing. I'll just show you that. And then I think you can see that the correlation is absolutely perfect. Beautiful. So as any of you out there are good at sketching, then please send in sketches as well as images, because it's a dying art. So many people are imaging these days, people are forgetting to draw, and it's magnificent to see these wonderful drawings coming into the section to be kept on record. So please have a go. Alexandra also sent in this magnificent animation, which she took a couple of days later on the 9th of May, and just look at that for a sequence. So we have a couple of prominences here, and you can see the plasma suspended in these field lines. Look at it rising into it, and then coming cascading back down here as plasma rain onto the chromosphere. Isn't that absolutely stunning? Thank you, Alexandra. Brilliant. And that brings me to the end of tonight's webinar. So if you've got any questions, I'll be glad to try and answer them anyway.
Well, Lynn, thank you very much for that. I always think it's quite disconcerting the lack of applause at the end of these talks, but I'm sure there would be plenty if we could hear it. So yes, we come to Q&A now. And if you've got a question, then click on the Q&A button. Well, if you're watching in Zoom, click on the Q&A button at the bottom of your screen, and you'll be able to type your question in. If you are watching on YouTube, then you should see a chat facility on the right-hand side of your screen. I see James Dawson has already started making use of that, and I will pick up your questions from there. And while you're busy typing, I will just put up the screen with the talks we've got coming up.
Want to stop sharing mine?
I think I can actually, because I'm in charge of this, I can actually force you to stop sharing. Yeah, so I think that should now be showing the list of talks. So next week, we've actually got a double bill. we've got a historical talk from Bill Barton about the BAA in Suffolk between the World Wars. And then we've got Nick James giving us a Skynote roundup. And then in 2 weeks' time, we have another talk from Nick James, who will be giving us a tour of the Comet section archives. Now, I see we already have quite a few questions. I mean, they've disappeared from my screen because
I can see some. I hope I've answered the one about the Thames freezing over. I mean, we don't know. I did talk to a solar physicist about the amount of solar radiation being received at the top of the Earth's atmosphere, and he said there wasn't really any sort of link to climate change, not one they know at the moment, and it wasn't a great difference between maximum and minimum in sunspots to make any significant difference. He seemed to think that the radiation received can have some sort of effect on weather patterns, but other than that, there's no real link to climate change. But again, it's a subject we don't know a huge amount about.
So we've had a question here from Diane, who wants to know if sunspots are depressions in the solar surface as we see it. Does that mean that are they a consistent depth?
No, they're not depressions at all. They have the appearance of depressions, but that's what it is. It's an illusion, basically. They're just darker areas because of the suppression of the energy rising up. I know when they get near a limb, they really do look like they've got a huge dip. That's the Wilson effect, but it is an optical illusion.
Now we've got a comment here from Jeremy Shears, who says, excellent webinar. Many people are reporting good white light results with Herschel wedges, for example, from Lunt or Beda. Any thoughts compared to front filters?
Well, I've got quite a few very good reports about Herschel wedges. The observers that use them absolutely swear by them. The amount of clarity they can see is fantastic. Unfortunately, I haven't looked through one personally, so I can't do a comparison. I don't know, Peter, have you had an opportunity to look through a Herschel wedge?
I have in the past, yes. And as you say, for visual viewing, then yes, some people really like them. In terms of front filters, then obviously there's the glass type that you showed earlier, and there's also the safety film ones. And again, people have preferences of glass compared to film as well. Of course, with the film ones, you need to be extra careful because they, if you're not careful, you can get pinholes appearing. Whereas the glass ones will last much longer. But they are more expensive to start with. So to a certain extent, it's personal preference, but just like yourself, Lynn, I have heard very good reports of Herschel wedges from a visual point of view.
Yeah. I don't know if you just switch your camera on, Peter, then we can see you. You're still blank. That's it. Excellent. Yeah. There's another question here. Would it be possible to predict the activity of cycle 25? I think I've answered that. Hopefully I've answered that sufficiently for you there, David. What other questions do we have?
We have a question from Richard Bottle, who asks, do we understand why the corona is so hot?
No, we don't. Well, there are two missions going out there at the moment, one from NASA, one from ESA, and they hope to give us a great deal more information about that. I think there has been something come back from the Parker Solar Probe to do with the solar wind as to why. I think it explains why the rotation of the sun is faster east to west than sunspots would seem to indicate that it is, and this is all to do with the heating of the corona. But I think we've got to wait a few more years yet when we get the information back from the Parker Solar Probe, because it's going to sample the corona. It's going to go very, very close in, up to about 3 million miles something from the sun, and actually sample it, and hopefully we'll learn a lot of science from that.
In fact, there was an interesting Sky at Night program fairly recently about these solar probes.
Yeah.
And they were saying that the poles potentially are the regions that are going to be important in heating the corona.
Yeah. I think that's the ESA mission is going to give us a view of the solar.
It is, yeah.
Yeah, it is. Yeah, I'm just seeing here a little short bit I've written down here about the Parker Solar Probe. It said a new paper suggests that sudden magnetic switchbacks in the solar wind have been observed by the Parker Solar Probe during its November flyby in 2018 and are tied to a theory first proposed more than 2 decades ago about how the sun's magnetic field migrates. So there we are. Science is coming in.
I'm going to move across to the questions on YouTube now. We've had a question from James Dawson, who asked if sunspots from the old and new cycles were in the same hemisphere at the same time, would their polarity be opposite?
Yes, they are. Yes, they are, because that's how we can tell the new cycle spots from the old cycle spots, because their polarity is reversed.
And David Armitage asks, who assigns the number to a new active region?
It's the Americans that do it. It's NOAA. Let me see if I can get this right. It's the National Oceanic and Atmospheric Administration. That's it. So they assigned it. They started up that category in January 1972 and it's been going ever since.
I see that Nick Nichols actually submitted an answer to that question as well, and he gave the same answer as you. So we definitely have consensus on that.
Oh, that's a relief.
Nick also makes a comment that one possible theory of why the corona is so hot is microflares.
Yeah. But Peter, have you got anything on that? Yeah, I've certainly heard of that. But...
Yes, I've heard about that as well. But hopefully these new spacecraft will answer these questions once and for all. But,
yeah.
So in the next few years, we should have some proper answers to that question.
Yeah, it's a sad state, but I'm going to do a Patrick. We simply don't know at the moment, but hopefully we'll find out soon.
So we have a question from Hugh Allen, who of course is a chemist, and he says that he's heard mention of observing the sun in sodium and even magnesium wavelengths.
Yes.
What is their interest over calcium K or hydrogen alpha?
Sorry, just see that last bit again.
What is the interest in observing the sun in sodium and magnesium as opposed to calcium K or the hydrogen alpha line?
Okay, well, there's not an awful lot of it going on. I don't know if Gary Palmer's here, but he's certainly images in sodium and all sorts of other different wavelengths. I think it's just a matter of companies trying out different wavelengths to see if they can, improve things or see something different or see something better. But at the moment, I don't think there's really a huge difference in the wavelengths from what we've already got in H alpha and calcium K line. Although the images that Gary Palmer submits in sodium are fantastic, and if you want to have a look on his website, then I'm sure you'll agree. Peter, have you got anything on that?
So I think that the sodium and magnesium, especially the sodium, you're still looking at the photosphere, whereas calcium K and hydrogen alpha, you're looking at the chromosphere, which is the thin layer above the photosphere. So certainly in hydrogen alpha, you can see far more activity, prominences and filaments and flares that Lynn has already shown. Whereas in sodium, you're basically seeing sunspots and granulation, albeit probably more detailed than you would in a normal white light image.
Yeah, the clarity that Gary gets in his sodium images are absolutely stunning.
Yes.
We have a question, how long can 2 solar cycles overlap?
It's not an exact science, several years. That's a matter of measurement. Like that the sun, it's like a solar cycle can last anything from 9 to nearly 14. Well, they can overlap again for an undetermined period. So 18 months, 2 to 3 years, I would say. I don't think certainly no more than that. I wouldn't have said, Peter.
Yeah, that's about right. About 2 years or so that they overlap. So it's not an instant change from one cycle to the next. It's an overlap of about 2 years or so.
Yeah.
So we have a question here from Thomas, who says this is a beginner question, but I think I don't actually know the answer to this myself. How do you observe the polarity of a sunspot?
Well, that's what we're calling a magnetogram. So you don't really observe it as such. You can go onto certain websites on the SOHO website and look at the magnetogram, and you will see it demonstrated there. I mean, I was showing a magnetogram, that black and white kind of grainy image when I was talking about polarity. So you can observe it on there.
Yeah, it's not a property that amateurs can observe. It's either done at professional solar observatories or from spacecraft, such as SOHO or the Solar Dynamics Observatory. But they have been measured for over 100 years now. So it's obviously the polarity, which is the key to the activity of a sunspot group, especially if it's a complex group. The magnetic field gets disturbed within the group, and you can end up by combining northern and southern magnetic material to cause a flare. So from a flare point of view, it's actually the magnetic field in the group is actually the important bit. But amateurs can't actually measure it directly.
There's a question here as to what data you're most excited to see from new spacecraft en route to the sun, and whether you're anticipating interesting data from the polar regions.
So yeah, I think we are excited to obviously firstly to be able to view the sun from just a few million kilometers, rather than here on Earth 150 million kilometers. Yes, as I mentioned earlier, it does seem to be that the poles are going to be the key to understanding the corona, and probably understanding how the sun works. Yes, so we are waiting for new data to appear.
There's so much about it we still don't understand, which is the fun of it all. So we've got high hopes on 2 probes going out at much the same time to bring us in a lot of information. Of course, there'll be a time lapse because they'll have to analyze everything and come up with theories and so on. But we're still, very excited about the next few years.
So we've got a practical question here from Diane, who says she's got a wedge and a mylar white light filter. With the wedge, you can see some surface cell detail that you cannot see with a mylar filter.
You're talking about the granulation that you can see?
I would assume so, yes.
Yeah.
I guess that's a comment rather than a question.
Yeah. That's what people tell me about the Herschel wedge. Again, it's the clarity of that is superb. I know quite a few people in the section that have got them, and one or two have written reviews, and all have been absolutely, very, very positive about them.
So Richard Bottle has another question about the polarity of sunspots. How does that relate to the North and South poles?
I'm not too sure what you mean by that. There's a North and South polarity of in the hemispheres of sunspots, and the sunspots themselves, have a positive and negative polarity. I'm not quite sure how I relate to that question. Peter, do you understand that one?
I mean, as Lynn mentioned, the actual solar cycle as determined by the magnetic field is actually 22 years. So in the northern hemisphere of the sun, you can get groups which are negative east and positive west in 11 years, and then they flip around in the other way. And obviously in the other hemisphere, they're flipped compared to the north. So each hemisphere is slightly different. Apart from that, I'm not quite sure.
We have a question from Jack Martin. How many elements are present in the sun? I guess the answer is an awful lot.
Yes, probably.
Yes.
Mostly hydrogen and helium, of course, but trace elements of most other stuff, I suppose. Yeah.
It's interesting to note that helium was discovered on the sun before it was discovered on Earth. There were absorption lines observed in spectra of the sun from an unknown element 100 and odd years ago, and eventually it was discovered to be helium on Earth. But yes, there are an awful lot of elements.
We have a question on YouTube from Nick Nichols, who asks if a Carrington event happened now, with us being more advanced and prepared, would it be a disaster like some experts predict, or are they scaremongering?
I don't think they are scaremongering. The Carrington event, 1859, I think it was. We have white light flares. They're probably a little bit more commonplace than we think they are. And white light flares, obviously, something you're observing the photosphere and you see a flare. It's rare-ish, certainly, but certainly worth looking out for. Because from time to time, I do get observers that think they've seen a white light flare. So we try and marry that up with anything that's happening in H-alpha to see whether or not there was a flare at that particular position. But certainly if something is bright enough to be seen in white light, then that's a pretty decent flare. The Carrington event would probably knock out, I think, a good deal of the hardware that we have floating up in space at the moment. I mean, there was a solar flare, the Canadian one, I forget the year that was, 2000, something like that, was it, Peter? I remember now. And that knocked out the grid in Canada. Yeah.
I think that was even in the late 80s, I think, wasn't it? 1989.
Can't remember the date.
Yeah.
From memory, in the 19th century, people were getting electric shocks off telegraph wires in the Carrington event. So you imagine that being plugged into electronics. I don't think it would be a good outcome.
No, it's a very real risk. And that's why the science of space weather has taken off over the last sort of decade or so. I know when I was doing solar astronomy, years and years ago, and I mentioned solar astronomy to astronomers, people sort of laughed and said, "Oh, that isn't astronomy, no one's really interested. You're a bit odd." But it's become very popular in the last 20 odd years. And suddenly with space weather, it's a thing to be in. So there we are.
So I think that is all the questions that we have at the moment. If anyone has any last questions, then please do type them in now. Otherwise, I will just finish off by saying that next week we have a double bill of 2 talks at the same time, 7 p.m. on Wednesday. We have a historical talk by Bill Barton about the BAA in Suffolk between the World Wars, and also Nick James presenting a Skynotes update. And then in 2 weeks' time, another talk from Nick James, who will be giving us a journey through the comet section archives. Now, I don't see any more questions, so I guess I'll have a quick look at chat, make sure I don't see any questions in the chat either. So I suggest in that case we wrap up, and I look forward to seeing everyone again same time next week.
Lovely, thank you. Thanks, Peter.
You're welcome.